Let's continue with rate limiting steps subtopic. What does it mean by rate limiting step? So rate limiting step can be defined as the step that has the slowest step. So the step that has the slowest step among the 7 heterogeneous catalytic steps which has been introduced to you before. So the lowest step will be the limiter and will the one that governs the overall rate of the reaction. Therefore, the classification of steps can be classified into two. The first one is the mass transfer steps. The second one will be the reaction kinetic steps. So the mass transfer steps is referring to step number 1, 2, 6, and 7. Why? Because step number 1, 2, 6, and 7 are the steps that involve diffusion, which is external diffusion from reactants going to surface of catalyst, and also diffusion from catalyst surface into the bulk fluid. Okay, so mass transfer is referring more to the transport phenomena steps, which is referring to step number 1, 2, 6, and 7. The reaction kinetic steps, the reaction kinetic steps are referring to step number 3, step number 4, and step number 5, because step number 3 is the adsorption of reactant onto catalyst surface. Step number 4 is the surface of reaction, the reaction surface, surface reaction. And step number 5 is the desorption of product and from the catalyst surface. So step 3, 4, and 5 referring to reaction kinetic steps. So as I said before, the rate limiting step is the slowest rate of steps among those 7 steps. So the slowest steps will actually govern, or will actually be the limiter for the overall reaction. So right now we are going to see which cases would actually be the limiter. Is it the mass transfer that will be the limiter, or is it the reaction kinetic that will be the limiter for the overall reaction? Jadi, kalau step 3, 4, or 5, as defined before, step 3, 4, or 5 is the reaction kinetic classification. If step 3, 4, or 5 is slower than step 2, 6, and 7, so meaning that the reaction kinetic is the limiter and govern the overall reaction. Okay, so it's stated here. If step 3, 4, or 5 is lower, so means that the reaction or overall reaction is under reaction kinetic limitation, and it is free from mass transfer limitation. Tetapi jika step 1, 2, 6, or 7, so step 1, 2, 6, or 7 as previously defined as mass transfer regime, mass transfer limitation, mass transfer steps. If step 1, 2, 6, or 7 is lower, than step 3, 4, or 5. So meaning that the overall reaction is under mass transfer or under transport limitation, and it is free from reaction kinetics limitation. So that's the meaning of rate limiting step. So this slide is just want to introduce to you the concentration profile. How does the concentration looks like when reactant is going to be near a catalyst particle. So it is represented by figure 7.9. So when reactant is about to migrate into catalyst particle, there must be a concentration difference between bulk fluid and also concentration near the external catalyst surface. So the concentration of bulk fluid is represented by the term of CAB, and then the concentration of the external surface is represented by CAS. And there must be difference also with the concentration within the pellets, and it is represented with CAX. The concentration of CAX, where X is the function of the catalyst inside of the catalyst, and the inside of the catalyst would have a different geometries, and later we will talk about how the geometries of the catalyst will affect the concentration CAX here. So next is we are going to determine whether overall reaction is going to be controlled by reaction kinetics. Okay, adakah reaction kinetics will be the limiter, or is it the overall reaction will be controlled by mass transfer? Okay, atau adakah external mass transfer will be the limiter that will govern, that will control the overall reaction. But before that, kita kena tengok mass transfer coefficient dulu. How to find the mass transfer coefficient. So the next few slides, I just briefly introduce to you on how to find the mass transfer coefficient, since you guys already learned this in previous subjects, maybe in transport phenomena or any other subjects that already introduced on the mass transfer correlations. So I nak you cari sendiri, recall sendiri on how to find this term, which is this is the mass transfer flux, and then this term is for mass transfer coefficient. And in order to find the term of mass transfer flux, you need to get the concentration difference. Okay, kemudian in order to find the mass transfer coefficient, transfer coefficient also can be found through the Sherwood number, in which Sherwood number ni you actually can find using convective mass transfer rate divided by diffusive mass transfer rate. I think this one is in heat transfer subject. So diffusion coefficient or diffusion rate is this term. Okay, and then this term, so meaning that the mass transfer coefficient can be found with this, using this term. Kemudian catalyst actually can be in flat, can be in sphere, can be in tube geometries, or can be in cylinder geometries. So previously, Sherwood number also you can find Sherwood number using depends on the geometry, flat plate, sphere, or tube or cylinder. So this theory can be used in order to find the mass transfer coefficients based on geometries of the catalyst. Okay, now still you need to recall on how to find the Sherwood number over a flat plate. So you kena recall this theory. So kena ada cari Reynolds number juga. Reynolds number kalau flow laminar, which is less than 10 to the power of 5, and then if the flow going over the flat plate, if the flow is turbulent, so the Reynolds number is more than 10.5. So you guys kena carilah Sherwood number tersebut. So nak cari Reynolds number, kena cari guna yang ini, teori ni, which is this is the velocity, this is the kinematic viscosity, and then you can find using the Smith number also. Kalau Smith number untuk gases is equals to 1. Kat situ nanti ni cara cari Sherwood number using geometry of a sphere pula. So ini adalah dia punya teori. So dia cakap kat sini kalau the limit of a slow flow over a sphere, we can assume that the Sherwood for sphere diameter will be 2.0. Which is it also can be used to diffusion from a sphere surrounded by a stagnant fluid. So kalau nak cari Sherwood number for flow through a geometrical tube, jadi Sherwood number you boleh guna yang ini jika the Reynolds number adalah less than 2100 kalau flow is the laminar, and if the flow is turbulent and the Reynolds number through the diameter of the tube, the Reynolds number is more than 2100, so you akan guna this theory. Kemudian kalau cylinder pula, the Reynolds number is less than 4, in which that it's the transition from laminar to turbulence, and it's around the cylinder. So the equation would be this one. And usually the Smith number for gases is 1. So again, kenapa kita cerita pasal catalyst with different geometrics just now? Sebab kalau reaction adalah mass transfer control. Kalau mass transfer control, kita perlu cari ni the mass transfer coefficient. So mass transfer coefficient actually can be found using Sherwood number and diffusivity of reactant A, and then divide by the length of the geometrical catalyst tersebut. And the Sherwood number here also depends on the geometry of the catalyst.